Well, for the first problem, I basically, well, firstly, I passed dt as a multiplication and t minus ta as a division. I integrated both sides, and on the left-hand side, I got the natural logarithm of t minus ta is equal to minus kt plus e, and then I get rid of the natural logarithm using the e, and well, I got the absolute value of t minus ta is equal to e to the power of minus kt plus e, and since it was two terms here, I could separate that in two e's. And well, the second one, e to the c, is another constant, so you can get rid of that and just write a c, so you can get the formula, the solution. Well, the absolute values you can get also rid of them, since the final temperature, well, not final temperature, the initial temperature is always bigger than the ambient temperature. This means it will be a positive. It cannot be a negative one, and it cannot have a negative sign. And then you got the final formula, but by passing minus Ta to the other side as a positive Ta, well, ambient temperature, and then you get the solution. For 1.2, well, firstly, C represents the initial deviation in temperatures. That means it determines how much difference there is from the ambient temperature to the initial temperature in this cool-down process. Well, to get the initial conditions, you have to assume that the time is equal to 0, like it's the initial values. And well, since e to the 0 is equal to 1, you just clear c out, and then you get that c is equal to the initial temperature minus ambient temperature, meaning that c in this case is the difference between the initial and the ambient temperature. And if c was to be a big number, it means there would be a big difference between t and ambient temperature, well, initial temperature and ambient temperature. If it was a little number, there would be almost no difference, graphically speaking. It would be like a really little space between them. And then for 1.3, well, I got C. I got that by putting the initial temperature value of 25 degrees and the ambient temperature value of 285, and I just cleared C out. And then when you have C, you now can get K. By clearing K out, you have to clear K out, you have to first pass the 285 as a rest, then you make the division. Since it was negative over negative, they turn positive. However, in the natural logarithm here, you have to get the natural logarithm from both sides, so you can get rid of the e, and the natural logarithm of this is a negative value. However, it will be also divided by a -1, or well, I have to get rid of the negative sign of k. However, in the formula, it is stated as minus kt, so the negative sign stays there, even though it changes a lot throughout the process. Well, I got this as my final k value, and this as the formula. Well, to get the value of time when the initial temperature is equal to 26. No, I mean, to get the value of time when the rod is to cool down to 26 degrees, you have to replace the 26 in the value of T, and you have to clear out T in the value of temperature, and then you have to clear out time by doing basically the same process you did with to clear out K, but now with T. So then you pass the 25 as a rest, then you divide this by 260, you get the natural logarithm, so you can get rid of the E, and then you pass this as a division, and by doing this in your Casio calculator, you get the 3251.2 seconds. Here is my MATLAB code for the problem 1. Here is the temperature of the oven, the ambient temperature, initial temperature. This is the K constant. Well, no, is the cooling constant. This is the this is the time vector going from 0 to 3000 by 1000. Here is the cooling constant C, and the heating constant C, and here is the cooling constant C. Here is the temperature over time for this heating process and the temperature over time for the cooling process, and here is the plotting both, and you get this. Then this is the 1.5 code, this other part. Well, this is the time step. This is the to make sure that the T value and the T cool are the same size. This is the this is to make, well, to initialize the to make zeros in the temperature vector. And this is the initial temperature of the aluminum rod, that is equal to 285. Well, here I have the function to make the Euler's method function, and here is the temperature rate of change, dt, and the temperature using Euler's method. Then this is to make sure that T cool is the same size, st, and here is the to graph them, and you get this. Well, for problem 2, well, basically to get the formula, the heat transfer formula, to as a function of time, well, firstly I divided both sides by t, by time, and since q over t is, well, since q over time is equal to pressure, I put the pressure there, and then I just clear the final temperature out by, well, passing the t as a multiplication, mc as a division, and the initial temperature passes it as a sum, well, as a positive number. And then I replace the values of the 1000 watts, the 0.8 liters, and the 3850 joules or kilograms times C. That is the specific heat of the seawater plus the initial temperature. And then I got this as my final expression for temperature as a function of time. That is 0.3247 times T, well, times time, plus initial temperature. And then well, this is the fifth degree polynomial notation, but, well, this represents the A0 represents our initial temperature, and the A1 times T represents our function here, the P over MC, that is also multiplicating T. And the higher degree terms are negligible, not only because, well, it's a linear function and linear equation, but also because they, as we discussed in class, they don't obey any underlying physics to get that formula, the higher degree formula. For example, for this formula, the transfer of heat, we got it by using physics. But to get this formula, you get it by using maths, but you cannot use physics to get this formula. So basically, the higher degree terms, polynomial terms, are negligible. And this is the MATLAB code for problem 2. Well, this is the power that they give us, the 1000 watts. This is the mass that they give us, the 0.8 liters. The specific heat of seawater, that is a little different from the specific heat of normal water. This is the time vector and the initial temperature value. This is the formula I got by clearing all that, and this is the to plot it and make the graph. It's like that. And this other side of the code is the second part, using the 5 degree matrix, the 5 degree as we saw in class. And, well, this is to have the coefficient, and time to make this times the coefficient, and basically you have this graph. And they might seem similar, but, well, as you know, the 5 degree terms make it look like that, not make it perfectly linear as this one. But, well, as we discussed, 5 degree terms are not physically, they have no underlying physics in them. Yes. Okay, for problem 3, I follow the calorimetry principle, which was it's basically that the quantity of your water minus the quantity of your copper is equal to 0, so you can balance them. And, well, it's basically this formula for the quantity of heat. And also the difference in temperature, it's the final temperature minus the initial temperature. But since the final temperature is the same for both, you can just write it like this for both cases. And it's also the wanted value, the unknown variable too. So, well, firstly I multiplied the mass, the MC times the values in the final temperature, initial temperature of both sides. So I got this, that is mass of water times specific heat of water times final temperature minus mass of water, specific heat of water times initial temperature, equal to the same for copper. And then I got the final temperatures on the same side, so I could factor it out, and the initial temperatures on the other side. So, well, yes, because we have to clear the final temperature out. So basically I got this as the factorization, after I factor the final temperature out, and I pass the value multiplicating the final temperature as a division on the other side, and this with the values that they give us is basically all this formula. And the specific heat of copper is 387 joules over kilograms MC, and specific heat of water is 4186 joules over kilograms C. And, well, after after performing this multiplication and, well, this division on the Casio calculator, I got this value as the final temperature, 77.12 degrees. It's actually centigrados, like that. Okay, for problem 4, well, basically you have to prove how this transforms to the final formula, that it's the difference in volume is equal to the weird B over here times initial volume times difference in temperature. So basically you have to, well, first you put the difference in volume formula for the cone, well, the right circular cone, that is basically this is the final volume formula minus the initial volume formula, and that is equal to the difference in volume. And then this expanded, it looks like this. You have to, well, first using basic algebra, almost forgotten algebra, you have to expand the r initial r plus the difference in r square by this, the r squared plus 2r times difference in r plus r difference in r squared. And then you get this as the formula. Also, we have to remember that the difference in r squared is negligible because it's basically, it's a very small value, almost zero. So it's basically negligible. And sorry if there's a lot of scratches, it's because I used that, I negliged a lot of things and canceled out on other things. So basically, you have to perform this multiplication first. And well, the first multiplication, that is 1/3 p times initial r squared times initial height, cancels out with this rest over here because this is negative, here is positive, they cancel out. It goes all the way there. And then the 1/3 times 2, well, that's 2/3 initial r times the difference in r times initial height plus 1/3 p. Well, this cancels out because, you know, it's negligible. Then this cancels out too because it's negligible, and this cancels out too because it's negligible. And then in the end, you get this formula. It's 2/3 p r initial r times the difference in r in radius times initial height plus 1/3 p r squared times a difference in height. And here you can factor out the 1/3 p r initial radius, times initial height. And when you factor it out, you get this on this, yes, in the parentheses, in parentheses, that it's 2, well, you have to also remember that the formula for difference in r or difference in height is the alpha times initial r times difference in temperature. And that's how you are going to get the final formula, the wanted formula. Well, basically here, this cancels out with, well, this cancels out with that one. And in the end, you sum this plus this is basically the same. And you get that the final formula for this is the difference in volume is equal to 3 times alpha times 1/3 p r squared initial r squared times initial height times difference in temperature, which actually is the wanted formula, since 3 times alpha is the b, that weird b, and this is the formula for the volume of the shape, the cone. And then for the 4.2, you just replace the value of the initial volume, the difference in temperature, the 3 alpha of the cone, and you get that the difference, well, the final volume that the object will have after the thermal expansion for these values that they give us is 10.57875 liters. That it's a little expansion in comparison to the initial volume. Well, for the final problem, well, firstly, it asks you if the temperature of the gas will increase, decrease, or remain constant. And in this specific process, the temperature will increase, since the initial state values for pressure and volume are lower than the final state values of the pressure and volume. The temperature value will also be lower in the initial state than in the final state. So it's an increase. And then to get work, well, you have to perform this integration. And basically, the formula for pressure is equal to the slope times volume plus C. That's the initial value. Well, basically, the slope can be written out like this, and to get, well, replacing the value that they give us for the final volume, the initial volume, the final pressure, initial pressure, you get this as the slope, that is 1 million, basically. And then you get C out, yes, you get C out by performing the clearance for C, that is basically the value of C is this one, that is a little, well, yes, 3 times 10 to the 4. And to get now the value for P, well, for work, you just replace the values gotten from the slope and from the C, and you basically get the integration for 0.11 and 0.07. Firstly for the left hand side, you basically, yes, okay, so basically you perform this integration of this formula right here, and you get basically this, that 1.10 to the 6 over 2 times b squared times 0.07 to the power of 0.11 plus 3.10 to the 4b times 0.07 to the power of 0.11. And then just performing these calculations with a Casio calculator, you get that, well, in the left integration, it's 3,600 joules plus the right integration, that is 1,200 joules, and that equals to 4,800 joules. That's the final work.